Hello, ladies and gentlemen. We're going to do 10.5 today. We're going to be talking about area and arc length in polar coordinates. And yes, I still sound like a frog. And the good news is this is our last video for Calc 2. Woohoo! So our objectives are that we're going to find the area of a region bounded by a polar graph. We're going to find points of intersection of two polar graphs, which is significantly easier than in our parametrics. And then we're going to find the arc length of a polar graph. Alrighty. So as we get started, I want to go back and review a little bit of information from geometry and pre-calc. So it's this idea of the area of, that was a nice straight line, a sector. Okay, so the area of a sector, which we have done before, is going to be 1/2 theta, and theta is going to be in radians, r squared, and we could do it in degrees also, but the formula is a little bit different, which is what you learned in geometry. But in pre-calc, this is the formula that we learned for the area of a sector, where remember r is going to be our radius, and theta is the angle with which I go through. Okay? Well, the same basic concept happens in polar coordinates. So the area in polar coordinates for a sector, okay, is going to equal 1/2, and then I'm going to have from alpha to beta, because we got to get all those cool letters in, of f of theta quantity squared d theta. And then we typically just simplify that to be alpha to beta r squared d theta. So it's actually not very hard. Okay, so let's do an example as we start off today for our last video. Woohoo! We want to find the area of one petal of the rose curve given by r is equal to 3 cosine 3 theta. All right, so a couple of things about rose curves to remember. Okay, this is going to be the radius or the length of the curves, and then because this value is odd, I'm going to have 3 petals. So if you graph this in your handy dandy grapher, use it in a different color, you would get a rose petal that looks kind of like that. And I shouldn't quit my day job for art. Alrighty, so we have some angles here, and then this one goes here, and this one goes here. So this is going to be pi over 6, and this is a negative pi over 6. So we're going to want to find the area of one petal, because all the petals at this point are going to be the same. So our area is going to equal 1/2 the integral from alpha to beta of r squared d theta. Alrighty. And so we're just going to do 1/2, and we're going to integrate from a negative pi over 6 to pi over 6. And then my r is 3 cosine 3 theta, quantity squared d theta. Now, on all of these problems, they get to be a little bit entertaining, and I'm just going to do a little bit of the math. Is that a good statement? And then at some point, we're going to just say enough is enough, and we would assume that you're going to be doing most of these in your calculator anyway. So at this point, I could do this in my calculator, but I'm going to go ahead and do a little bit of it just because it's good for our brains to exercise our trig. And I'm going to have 9 cosine squared 3 theta d theta, which means I get to bring that little guy out front, negative pi over 6 to pi over 6, and then I have cosine squared 3 theta d theta. Alrighty? So then I'm going to bring in a power reducing identity, and then I think at that point we'll simplify it, and then we'll call uncle, and we'll do the rest of it in our calculators. So here's the 9/2, and then I have a negative pi over 6 to pi over 6. And then if I use the power reducing, which doubles this angle, so this guy's going to become a 6, it's going to be 1 plus the cosine of 6 theta over 2 d theta. That 2 can come out, and at this point, right after this, I'm going to call it quits. So it's 9 over 4, negative pi over 6, pi over 6, and I have 1 plus the cosine of 6 theta d theta. And it actually, at this point, isn't really very hard. But again, I'm going to assume you're brilliant, which you are, and we're just going to finish this in our calculator because I would do U substitution for this guy, so that's not so bad. So this isn't horrible. So at this point, we would move on, and we're going to say this is all equal to 3 pi over 4. And I want to identify my answer, but I'm going to come back up here because I ran out of room. So the area of one petal is going to be equal to approximately equal to 3 pi over 4. So that one wasn't horrible. All right. So the next thing we want to do is talk about what happens with some of these really cool polar equations when things start overlapping and do like an area between the curves. So I want to, in this example, find the area of the region lying between the inner and outer loops of a limacon, which is the polite name for a butt graph. And our equation is r is equal to 1 minus 2 sine theta. Okay, so this one could be also called a cardioid with an inner loop. So if we look at the graph, okay, so it's going to be, here's the outer loop, whoop, and then it's going to have an inner loop. Okay, it's really kind of a crappy picture. But, so if we look at this information, this is going to be pi over 6, and this is going to be 5 pi over 6. And we're actually looking for the area in between those two curves. Alrighty? So the area of the shaded region is going to equal the area of the whole minus the area of the whole, as we go back to chapter 7 from our book. Okay? Alright. So then the area of the shade is going to equal the area of the whole. So here's going to be the 1/2 integral, and we're going to integrate from 5 pi over 6 to 13 pi over 6, and we're going to do 1 minus 2 sine theta quantity squared d theta. And so the 5 pi over 6 to the 13 pi over 6 gets us the whole cardioid, okay? And then, sorry, I was just looking at my math to make sure I hadn't screwed something up. And then I'm going to take away the little guy, and the little guy is going to be from pi over 6 to 5 pi over 6. And then we do the same curve, 1 minus 2 sine of theta, quantity squared, d theta. Almost fit on the page. And then at this point, I would tell you to use your calculator. You could do it by hand, but I would just tell you to do it in your handy-dandy calculator, because my assumption is at this point, you would have a calculator at your disposal to pull these problems off. Let's go back and talk about something that we've talked about before, because that little chunk of math gives you some good information. The maximum radius for this particular curve is going to be 1 plus 2, which is 3. So from here down to here would be 3, okay? And then if I subtract 2 minus 1 to get 1, that says the radius in here is going to be 1, because that's your minimum radius. So that's just cool little pieces of information about our limacons. So the area of our shaded region, after we do some brilliant math and button pushing, is 8.34, and that would be our area of the shaded region. Alrighty, so now what's going to happen is we're going to talk about intersecting graphs. My pen just exploded a little bit. Alright, so let's say, and I'm going to actually show you this one on the calculator in a minute because it just is gruesome by hand. So let's say I have the curve 1 minus 2 cosine theta. So I know my maximum radius is 3. I know my minimum radius is 1. I also know that this curve is symmetric about the horizontal axis. And then r equals 1. This little guy is a circle. Well, I just happen to have it in my handy-dandy grapher. I think maybe you can see it. And so I'm going to hit graph. Whoa, there's such a wicked glare. Let me see if I can find a spot where you can actually see it. Wow. See if I can turn that light away so you can actually see it. Wow, that's just terrible. Huh. It's just not so happy. I'm having a hard time finding a place where it can see it. All right, even though it's crappy, I think you get the general idea. So I basically have a limacon with an inner loop, and then I have my circle. So they intersect at 1, 2, 3 points, okay? So I'll sketch that on our paper just so we have something to look at. No laughing at my hideous graphing capabilities. So this is our limacon with the inner loop. And then our circle is going to go through here, here, here. Oh, that's a lovely circle. So notice that I have 1, 2, 3 points of intersection. So unlike when we were doing our math with our parametric equations and we're struggling to find those points of intersection, it actually works fairly politely in polar coordinates to find that point of intersection. It does have a little bit of an issue though, and I'll talk about that one in just a sec. So I'm going to set these two curves equal, so 1 equals 1 minus 2 cosine theta. The 1's cancel, and so I get 0 equals a negative 2 cosine theta. 0 equals cosine theta. Seems sacrilegious to do my math in this direction. And so theta, cosine is 0 when theta is pi over 2 and 3 pi over 2. So that takes care of that one and that one. Okay, so we got those 2 points of intersection in, but this guy is the problem child, and we can't find that third point of intersection. So you just have to be super careful to be able to find those points of intersection and make sure that you've gotten all of them. And so you want to use your grapher, which again I'm assuming you're going to have access to, and you would want to use your grapher to find those points of intersection. Alrighty, so the next example, we're going to do another example, about find the area of the region common to the 2 regions bounded by the curves of r is equal to a negative 6 cosine theta and r is equal to 2 minus 2 cosine theta. But before we do that, I want to go back to the previous problem because I just remembered that I should probably tell you this. Notice we talked about that the circle has a radius of 1. So this point right here has coordinates 1, comma, negative 1, comma, 0. Okay, because remember I do the angle and then the radius. So if this is 0, and then I use my negative 1 to pop me to the other side of the circle, I can actually get the coordinates of that coming from here, but if I hadn't had access to my grapher to look at that picture, that would have been difficult. All right, so let's put these 2 equations, and maybe it can show up better. That's just really nasty. I don't know. I give up. All right, let me see if I can turn that guy off, and maybe that will be better. Where's his little switch? Can you see it better? no. And now everything is just dark. So let's just turn it back on. All right. So I'm going to go ahead and put the equations in, and then we'll do the best that we can. I want to do this one first. -6 cosine theta. And then remember, this one is a circle, and it's been moved along the x-axis or the horizontal axis, right? And this one would actually be moved to the left. So that's actually pretty easy to find. And then this one's 2 minus 2 cosine theta. Okay. This one is a limacon, and it has, it doesn't have an inner loop because A divided by B is 1, and it's also going to be symmetric about the x-axis. So I'm going to graph it. All right. I'm going to do zoom 3 inner. There's the circle, and there is my cardioid. Okay. All right. And I know you can't see it very well. I can see it just great. But here's kind of what it looks like. So you can put those in your calculator and see better. So I have, this guy is the circle, and then over here, this is the -6. So technically the radius is 6, right? And then I have my cardioid, and he's going to intersect something like that, okay? So if I think about what I have, this is 2 pi over 3, and this is 4 pi over 3, okay? So a couple of things to notice. Both of these graphs are symmetric about the x-axis. So if I'm trying to find the common area, I can find the area in between this guy, and we're going to call him pink. And then I can find the area between the curves from here to here, the purple guy, right? And then I can double that area. Does that be better? Not really. There we go. Now we're back in business. Then I can double those two areas. All right. So, let's see. This little guy in here, my pink one, is going to go from the 2 pi over 3, okay? So he's going to go from 2 pi over 3, and it'll get me in here. So I'm going to go, brain and mouth, pi over 2 to 2 pi over 3. And then to get my purple guy in here, I'm going to go from 2 pi over 3 to pi. And then I'm going to double those areas because it is symmetric about each axis. So then remember that the area is equal to 1/2 the integral from alpha to beta of r squared d theta. And then because I do have an image that is symmetric, I'm just going to double it. So if I write my equation, and I'll attempt to do it in my color coordinated pens. Here we go. So the first thing we're going to do is my little pink slice. And so he's going to be 1/2, and I'm going to go from pi over 2 to 2 pi over 3. And then the negative, this one right here, this little slice comes from this radial line at 2 pi over 3 and the circle. So this one's going to be the -6 cosine theta quantity squared d theta. And then the rest of it plus, and then I'm going to have 1/2 the integral from 2 pi over 3 to pi. This one is determined, this little slice is determined by the cardioid, okay? So the purple is going to be part of the cardioid. This was bound by the circle and the radial line. This part is bound by the cardioid and the radial line. So this one's going to be the 2 minus 2 cosine theta quantity squared d theta, okay? And at this point, we're going to say hallelujah because we have access to a grapher, and we're going to write down that our area is approximately equal to 5 pi. You do want to make sure that you're careful when you put these in your grapher that your calculator is in radians so that you get the appropriate values. All right, so that takes care of that little guy. You do have to be pretty careful to decide which piece is being bound by which particular curve. So again, pictures are helpful. Your calculator is glorious. So the last formula that we get to learn is arc length in polar form. Okay, not so different from the other ones that we've seen. So our arc length is equal to the integral from alpha to beta of the square root of f of theta squared plus f prime of theta squared d theta. And then we simplify that to be the integral from alpha to beta square root r squared plus dr d theta quantity squared d theta. All right, and this is the form that we're going to use. And I'm going to show you a little bit of the trig identity work on this one to a point, and then I will bail because it is good to practice using our identities just a little bit. So we'll get a new sheet of paper because we got a lot of trig to do. So the last example says, find the length of the arc from theta is equal to 0 to theta equals 2 pi. So we're going to do, and I guess you can't see it, one complete revolution for the cardioid. Okay, and our cardioid, I'm going to draw the graph first and then I'll give you the equation. It's going to be a cute little guy, no inner loop. So that's going to be r is equal to 2 minus 2 cosine theta. Alrighty. So a couple of things to notice. If you were to put this in your grapher, the maximum radius is going to be at 4. Okay. 2 minus 2 is 0, so I don't have an inner loop. I don't have a minimum radius. All right. So from here, I'm going to go ahead and do dr d theta. And if I do dr d theta, I get 2 sine theta. And so now I'm just going to substitute in and use my equation. I usually rewrite it just because it's good practice. So I have alpha, that's an alpha, to beta. I like betas. I think they're kind of cool. R squared plus dr d theta, quantity squared d theta. Okay. So if I set my integral up, it's going to be the integral from 0 to 2 pi because they told me that it's going to go one complete revolution, right? And then I'm going to have my r, which is 2 minus 2 cosine theta, quantity squared, plus 2 sine theta, quantity squared. All of that's going to be under the radical d theta. And I'm going to do the math on this one a little bit, just because it cleans up fairly politely to a point, and then we'll use our handy-dandy graphers. So now I'm going to have the integral from 0 to 2 pi square root of, and I'm going to square all this mess. So I'm going to get 4 minus 8 cosine theta plus 4 cosine squared theta plus 4 sine squared theta. Ooh, that should look promising. D theta. Okay. I'm going to factor out a 4. So I have the integral from 0 to 2 pi. I'm going to factor out the 4. I'm not going to take it out just yet. And I have 1 minus 2 cosine theta plus cosine squared theta plus sine squared theta d theta. Alrighty. If you'll remember from your trig, cosine squared plus sine squared is 1. So now I'm going to take him outside. So here's the 2, 0 to 2 pi. See if you can still see what I'm doing. And then I have the square root of 1 plus 1 is 2 minus 2 cosine theta d theta. I'm going to factor out the 2. And I'm going to go ahead and pull it out. I'm going to save a step because if I factor out the 2 on the inside, I'm going to have a 2. And then I'm going to have 1 minus cosine theta. And I'm going to take the radical 2 out. So I'm going to have 2 radical 2, 0 to 2 pi. And then I'm going to have 1 minus cosine theta d theta. Now, this is where the problem gets weird and they start bringing in some tricky identities. So we're going to write that we're going to do some trig identity loveliness, loveliness, maybe. We're going to whip out our handy dandy graphers and we're going to get the arc length is 16. How was that for some trig identities? All right, ladies and gentlemen, we are done. Calculus is finished for BC. See you soon.